This lecture deals with measures of association for nominal and ordinal variables. Key terms include proportional reduction of error, or PRE, lambda, and gamma. So what are measures of association? Well, they're single numbers that are used to summarize the strength and direction of the relationship between two variables. And they're measures that reflect the level of utility in using one variable to predict the value of the other variable. Measures of association are usually thought of under the framework of something called proportional reduction of error, or PRE. It's a formal comparison of two quantities, E1 and E2. E1 refers to errors made in predicting the value of the dependent variable when the independent variable is ignored, and E2 refers to errors made in predicting the value of the dependent variable when the independent variable is used. As an illustration, consider the following example. Suppose that you wanted to predict somebody's race based on their residence, and imagine that you didn't know their residence. Suppose all you knew was that somebody lived in the United States. What would you guess is their race? Well, you would probably guess white. Now suppose you were told that that person lived in Harlem, New York. Would that change your guess? It probably would, because most people in Harlem are black. So the question is, how much better is your guess if you know their residence versus if you don't? And that's the idea behind PRE. Formally, it takes the difference between E1 and E2 and divides it by E1. And it basically tells us how much better is our guess if we have information on the independent variable versus if we don't. PRE measures often range from either 0 to 1 or -1 to 1, depending on whether or not we have ranked variables. 0 indicates that the two variables are not associated at all. That is, having some knowledge of the independent variable gives us no utility in predicting the value of the dependent variable. And then a value of negative or positive 1 indicates a perfect positive or negative association. PRE measures usually take on an intermediate value between 0 and negative or positive 1. Larger departure from 0 in either direction indicates a stronger association, whereas values closer to 0 indicate a weaker relationship. You can see that here strength and direction are actually independent. That is, you could have a strong negative association, a weak positive association, or anything in between. And we usually multiply the measures by 100 and express them as a percent. Let's start by talking about lambda. This is a measure for nominal variables. It ranges from 0 to 1. 0 means that there's no association. 1 means a perfect association, and it usually takes on values between 0 and 1. Lambda is an asymmetrical measure, meaning that it matters which variable you choose as the independent and dependent variable. It's sensitive to the choice of the two, and will give you a different answer if you reverse them. Here's the formula for lambda. The Greek letter lambda is used to refer to the measure itself. And in the numerator is E1, which is the errors in prediction when we ignore the independent variable, subtracted from E2, which are the errors in prediction when we use information on the independent variable. And the difference there is divided by E1. As a concrete example, let's look at the association between church attendance and sex. In order to calculate lambda, we'll have to use 3 steps. The first is to calculate E1, the second calculates E2, and the third plugs them into the formula and computes the measure. So, here's a bivariate table showing the relationship between sex as an independent variable and church attendance as a dependent variable. How do we calculate E1? Well, we have to look at the distribution of the dependent variable, which is here shown as the row marginals. We have to find the modal category here, which in this case is infrequently, because we see that 566 people report infrequently attending church, and that's the highest category. Now we ask ourselves, how many errors would we make if we assumed that everybody responded according to the modal category? That is, how many errors would we make if we assumed everybody infrequently attended church? And we can see that there's a total of 1,966 people. So if we subtract the modal category from that 1,966, we would get the number of errors that we would make, or E1. And so that's equal to 1,966 minus 566, or 1,400. And so E1 is 1,400. Next, we have to calculate E2, errors in prediction made when we use more information on the independent variable. And so what we'll do is we'll do the same process separately for the categories of the independent variable, that is, separately for males and females. And so what we have to do is we have to identify the modal category for both. And so for men, we can see that infrequently is the modal category, because 268 of the 883 men report infrequently going to church. For women, it's regularly, because 319 of the 1,083 report regularly attending church. And so we ask ourselves, how many errors would we make if we assume that all men went infrequently? And how many errors would we make if we assume that all women went regularly? And to find that difference, we just take the column total and subtract the modal category. And so for men, it would be 883 minus 268. For women, it would be 1083 minus 319. When we add together those two differences, that is 615 and 746, we get 1,379. And that's the number of errors that we make, or E2, when we take into account the value of the independent variable. Now we can plug those two numbers into our formula. And so recall that E1 was 1,400 and E2 was 1,379. Here we ask, how much better is our guess if we have the information on sex than if we don't? And we can see that the difference is negligible. And so if we take the difference between E1 and E2, we get 21. And then if we divide that by E1, or 1,400, we get a value of 0.015, which, expressed as a percent, tells us that there's a value of 1.5%. And so how do we interpret that? Well, we can see that there's a weak association between sex and church attendance. And so we can say that having information on somebody's sex improves our guess about their church attendance by about 1.5%. Now you might be wondering, why is it so low? Well, there are several factors that influence somebody's church attendance, and evidently sex isn't one of them. And so we should have taken into account other factors if we wanted to know why people attend church. But it doesn't seem like sex is something that really can differentiate between regular or non-regular church attendance. Now we'll talk about gamma. Gamma is a measure of association for ordinal variables, and it ranges from -1 to 1. Because it uses ordinal measures, notice that it tells us both about the strength and the direction of the association. And gamma is an example of a symmetrical measure, meaning that it's not sensitive to the choice of independent or dependent variable. That is, if you reverse the two, you get the same answer. Gamma is based on a calculation of pairs of cells. And so take a look at the following table. It shows a hypothetical relationship between two variables, variable x and variable y, both with two categories, a high and a low category. In the calculation of gamma, we have to find all the cells that have either a positive or a negative relationship. And so which combination of or pairs of cells here have a positive relationship? Recall that a positive relationship means that as we increase the value of one variable, we're also increasing the values of the other variable. That is, we're looking for a combination of cells that are high on both variables and low on both variables. And notice that cells 1 and 4 give us that combination, because cell 4 is low on both x and y, and cell 1 is high on both x and y. And so you can see that as we go from cell 4, we're going from low on both to cell 1, high on both, and that's a positive association. Where do we find the negative association? Well, we can see that cells 3 and 2 combined show a negative relationship, because they show that as the values of one variable increase, the values of the other variable decrease. In other words, as we go from cell 3 to cell 2, we're going from low to high on variable x to high to low on variable y, and vice versa. And so that shows a negative relationship. Notice that the other pairs of cells don't have any direction. So if we look at 1 and 2, 2 and 4, 4 and 3, and 3 and 1, they're tied, and therefore they're not used in the calculation of gamma. Only cells that have positive or negative relationships are used in the calculation. Let's switch gears for a moment. Let's suppose that instead of using 1 through 4 to identify the different cells, let's say these numbers are actually cell frequencies. In other words, let's say that we have 1, 2, 3, and 4 people, respectively, in each of these different cell combinations. Let's suppose that we pick two cells. How do we know how many unique pairs of cells are found across the combination of these two cells? Well, to answer that question, let's suppose that we assigned a letter value to each of the 5 people involved in the combinations of cells between 1 and 4. So let's say that we call the person in cell 1 A, and we call the 4 people in cell 4 B, C, D, and E. How many unique combinations can we make across these two cells? Well, we can see that we compare A with B for our first combination, then with C for our second, then with D for our third, and then with E for our fourth. And so there's 4 unique combinations. Notice that we could have gotten this by multiplying the cell frequency in the first cell by the cell frequency in the fourth cell, or 1 times 4. In general, gamma uses pairs of cells in its calculation, not just the direction of the cell, but also how many unique combinations are across each of those cells. And so formally, it's a comparison of two quantities, ns, the number of same-order pairs, or the number of pairs of cases that have a positive association, and nd, the number of inverse-order pairs, or the number of pairs that have a negative association. And to calculate gamma, we use the following formula. We find that gamma equals the difference between the same-order and inverse-order pairs divided by their sum, or ns minus nd divided by ns plus nd. To give you a sort of intuitive sense of how gamma works, suppose that we've zeroed out some of its values. For example, suppose that we had no inverse order pairs, or nd equals 0. You can see what we're left with is ns in the numerator and ns in the denominator, which equals just positive 1. Now suppose that we had 0 for ns, that is, there were no same order pairs. Well, we would be simply left with negative nd in the numerator and positive nd in the denominator, which comes out to negative 1. So you can see at the extremes, gamma takes on values between negative 1 and 1. To take a look at the calculation of gamma, let's look at the example of the relationship between a father's highest degree earned and a respondent's highest degree earned. We can use ordinal measures from the General Social Survey, which I've recoded to both be 3-category measures to make the calculations a little bit more simple. So, the following table shows a bivariate frequency distribution of father's highest education and respondent's highest degree of education. In order to calculate gamma, we have to calculate the number of inverse order and number of same order pairs. But before we can do that, we have to figure out where on this table we have a positive and negative relationship or association. And so to do that, what we have to do is we have to identify the high values and the low values for both variables. So you can see that some college or beyond are the high values for both, and then the low values for both are less than high school. And so that means that if we want a positive relationship, we have to go from the top left-hand corner to the bottom right-hand corner, which is where we find that low values of high school are going together and high values of degree are going together. In other words, when we go from low education to high education for fathers, we're also going from low education to high education for respondents, and that's a positive association. Now, where would we find a negative association? Well, it would just be the opposite, from the bottom left to the top right. And that's where we find low values of father's education going with high values of respondent's education, and vice versa, and that's a negative relationship. To calculate the number of same-order pairs, we start by finding any combinations of cells that have a positive association. And so we should start at the top left-hand corner, and then anything below and to the right is going to have a positive association. So how do we get the number of unique pairs across this combinations of cells? Well, all we have to do is just add the contents of the 4 cells that have a positive association with the focal cell. That is, we add up 6, 24, 20, and 203 to get 253. And then we multiply that by the cell frequency of the focal cell, or 801. And so when we do that arithmetic, we get a value of 202,653. But we're not done yet. There are still more cells that we have to consider. So we move on to the next cell, and we notice that this cell has a positive association with these 2 cells. And so if we add those together, 24 plus 203, and we multiply it by the cell frequency of that focal cell, 33, we get 7,491. Notice that we can skip the next cell because it has nothing below it and to the right. In other words, we don't use the marginals or the totals in the calculation of our measure. So we move on to the next row, and we see that the first cell in this row has a positive association with these 2 cells, the ones below and to the right. And so we just add those 2 together, 203 plus 20, and we multiply it by 82 to give us 18,286. And then we move on to the next cell, which has a value of 6, and we multiply it by 203. And that gives us our last same order pair, because notice that all the other remaining cells have nothing below and to the right. So 6 times 203 gives us a value of 1,218. And so notice that if we add all the same order pairs across all the 4 cells that we looked at, that is, if we add 202,653 to 7,491 to 18,286 to 1,218, we get a total of 229,648 same order pairs. So that's NS. Now we have to find ND, the number of inverse ordered pairs. And we'll start at the top right. Any cell with a negative relationship is going to be below and to the left of that cell. And so we just add up the cell contents of those 4 cells, 82, 6, 273, and 20, and we multiply it by the value of the focal cell, in this case 80, and that gives us 30,480. But we also have to account for every other cell, and so we move on to the next cell, and we find that it has a negative relationship with two cells. We add up their cell contents, 82 and 273, multiply it by 33, and we get 11,715. The next cell has nothing below and to the left, so we can skip it. So we move on to the next row. And so we can see that this cell has a negative relationship with two cells, the two that are below and to the left. And so we add the two together, 273 and 20, and we multiply it by 24, and we get 7,032. The next cell has a negative relationship with only one cell, and so we multiply the two cell contents together, we get 1,638. Notice that we don't have to consider any of the other cells because none of them have a negative relationship. That is, nothing is below and to the left of any of the other ones because we can't take into account the row totals or the column totals. So if we sum the total number of inverse order pairs across those four cells that we just calculated, that is, if we add 30,480 to 11,715 to 7,032 to 1,638, we get 50,865. And that gives us the total number of inverse order pairs, or the total number of unique combinations of things that have a negative relationship. So now we can just plug those values into our formula. And so recall that NS was 229,648. ND was 50,865. To calculate gamma, we would just take their difference in the numerator and divide it by their sum in the denominator. And when we do the arithmetic, we get a value of 0.63. So how do we interpret that? Well, we can say that there's a positive and moderate association here. That tells us that as father's degree gets higher, so does respondent's higher degree. And that makes sense. We think that people with more educated fathers are themselves more educated. But it also tells us that if we have knowledge about a person's father's education, that improves their guess of their own education by 63%.